bases and pH and pOH and all of those sorts of things. But before we get into doing calculations and other stuff like that, let's just talk a little bit about the phenomena of acidity. Now, of course, everything begins with water. We talked about water last chapter. We said that the covalent bonds in water were polarized because we have differences in electronegativities. 2.1 for hydrogen, 3.5 for oxygen. This leads to a molecular dipole where we have a positive end of the molecule down here and a negative end. This is the electrostatic potential map. And once again, blue stands for the absence of electrons. Excuse me. Blue stands for the absence of electrons, red for an abundance. So we have positive end and a negative end. We saw that this was very important because it allowed water to do things like dissolve ionic compounds. When we have a cation and an anion in solution, for example, the anion will be wrapped with water molecules with a positive end facing it, and the cation will be wrapped with water molecules with the negative ends all facing in. This distributes the charge and makes it much more stable. Now, water is a polar molecule. It has a positive end and a negative end. This allows it to react with charged things. Doesn't it make sense that water should also be able to interact with itself? So here's a lonely water molecule just sitting there. Once again, we have a hydrogen here and here, oxygen up there. These are positive, and that's negative. If we bring a second water molecule up to it, something like this, we can orient this so that the oxygen end, the negative end, is pointing at one of these hydrogens. And when it does, it forms a bond, a weak bond. We call this a hydrogen bond. It's about 5% of the strength of a covalent bond, but still, as we'll see, it's really quite real. We have more charged centers in this molecule, so we could easily bring another water molecule up and do the whole thing all over again. I can bring in a third from the top and make these 3 hydrogen bonds off this one water molecule. Now, if you think about this, we still have 2 hydrogens here, 2 here, 1 here, we have an oxygen up here. We can extend this network basically as far as we want. This is more or less what you're seeing here in a better 3D. Here's our water. We can put a couple oxygen, hydrogen bonds in here, like this, a couple more hydrogen bonds here. This rendering is actually very, very interesting. This is a calculation of what a cluster of water molecules might look like at any one instant. Now we draw hydrogen bonds like this, long, dashy things, sort of whatever. But if you look at this rendering, it goes a lot more than that, doesn't it? I mean, look at these guys. This is essentially half swallowed that hydrogen, hasn't it? And the same thing, you can see it all over. This is an awful lot of very, very powerful interaction. And even though each of them is very small, when you sum them all together, This is one of the things that gives water its amazing properties. Its ability to form extended hydrogen bond networks. Any questions? Well, I want you to think a little bit about, say, this hydrogen between these two oxygens and whatever, just kind of living there and being half swallowed by somebody else. And let's consider just a pair of water molecules sitting here, hydrogen and bonding. We know that this is a weak interaction, but there are a lot of them. If we take this pair and we put in just a tiny, tiny touch of energy, thermal energy, whatever, shake it up, look at it funny, what can happen is that this hydrogen can actually move along this hydrogen bond and be transferred to the other water molecule. Now when we do this, we have made H3O, that's called a hydronium ion. And we have made hydroxide, OH minus. Now, they're still sitting here. They're still hydrogen bonding. Hydronium could easily hand this hydrogen back. And we're back to two waters, simply hydrogen bonded. I can do this over and over again. But the bottom line is that this process, I'm sorry?
Can you drink it? Hydronium? Is that possible?
Hydronium, right, H3O plus.
Oh, it's like really good water.
Yeah, it's there in water. H3O plus and hydroxide. This process goes on constantly. That is, we transfer hydrogens back and forth, so that at any instant in time, if you looked at water, you looked at a sample of pure water, there would be 1 times 10 to the minus 7 molar hydronium and hydroxide. This is referred to as the autoprotolysis. If you have absolutely pure water, most of it is just plain old H2O, but there will always be 1 times 10 to the minus 7 moles per liter of hydronium and hydroxide. Now that's kind of neat. That's kind of neat. Water is able to split its neighbor, form 2 charged species. Now these charged species really are charged. This is electrostatic potential map for hydronium and hydroxide, and you can see the extent of the color in these things. We know that nature doesn't like charged particles, but this most certainly is very dark blue and very, very, very red. The reason that this process can go on at all, as we've said before, is that water is capable of stabilizing these charges. This is hydronium, H3O, positive charge. We're looking down at the oxygen. Instead of a nice red top, we have kind of a pale green top. And as you can see from the side, we have a huge blue bottom down here with these 3 hydrogens. Very, very charged particle. But this is sitting in water. Now remember, water has the ability to take a charge and disperse it. It works for sodium, it works for chloride, it works for all ions, but it works really well for something like hydronium and hydroxide. Let's take our hydronium, this guy, surrounded by 3 waters, only 3, and we're going to calculate the electrostatic potential map. So here's the hydronium we start with. When we calculate the map for the whole cluster, we wind up with something like this. Instead of our blue spot here, we actually have green and yellow now. And the whole point of this, once again, is that water itself is capable of dispersing this charge. That's why this happens. And water is the only thing we know of that can do this. Now, I mentioned that there typically are more than 3 waters around a charged thing. Here I put 8 waters around. Right here in the middle is our hydronium. So I'm going to do the same exercise. I'm going to calculate the electrostatic potential map over the whole cluster. Keep your eye on the guy in the middle here. Because when we do this, the guy in the middle not only has not a trace of blue anywhere, but it's got a nice big red cap on it. Now once again, this is where it is. But the 8 adjacent waters are capable of taking that charge and essentially dispersing it everywhere. One of the amazing things that water can do. Any questions? Now, we said that a consequence of the hydrogen bonding was the fact that water was able to take one of the bonds to one of its neighbors and break it, break the covalent bond, and make 2 charged species. That's kind of a noble undertaking, really. But it turns out that water can do it on lots of different molecules, not just itself. Let's consider our friend hydrogen fluoride. Remember hydrogen fluoride? We had a covalent bond here between the hydrogen and the fluorine that was very, very highly polarized. Fluorine is the most electronegative element, and it sucks the electrons in the covalent bond towards itself, leaving this bond for the hydrogen relatively weak. So here's a simple animation of a water molecule hydrogen bonded to an HF. Just like we saw with water bonded to itself. And the same thing can happen. The slightest bit of energy put into the system, this hydrogen can be transferred from HF, breaking the covalent bond to form hydronium and fluoride anion. What we have done is taken the polar covalent bond, we have broken it, we have formed an anion and hydronium ion. This is the concept of acidity. When we say an acid in solution, we're talking about the presence of hydronium. H3O plus, this guy, is what we mean when we say an acidic solution. Any questions? Yeah.
So if you want to make the super water,
You have to talk loudly.
if you want to make like a super water, you wouldn't want acid to make water, right? So like, how would you do it? How could you make a super water, like an H3O without the flow?
How would you do it?
Yeah.
Well, it happens spontaneously. The autolysis of water basically happens 10 to the 8th times per second. So if you have two water molecules sitting there, you know how I handed the proton back and forth? That really goes on 10 to the 8th times per second. Very, very fast process. This is constantly going on in water, everywhere. All right, so this is a chemical equation for what we just saw. Hydrogen fluoride with its highly polarized bond plus water gives us hydronium and fluoride anion. Now, just like we saw with water, H3O plus can hand this back, can't it? So we have two processes going on. A forward reaction where we ionize, and a back reaction where we take H3O plus and fluoride and reform HF and water. Both of these reactions go on at the same time, simultaneously. Once again, 10 to the 8th times per second. Very, very fast. When we have reactions that go forward and in the reverse at the same time, we call this an equilibrium. We show an equilibrium reaction with a special arrow. It's a double arrow. Now, it's not a double-headed arrow. That's for a different thing. But this is one arrow going this way, one arrow going this way. Whenever you see this, it tells you that the reaction goes both ways, this way plus this way, very rapidly in real time. It's an equilibrium. We call this the equilibrium dissociation of HF. We're going to form hydronium. Once again, whenever you form hydronium, H3O plus, that's an acid. HF is hydrofluoric acid. Something that has an acid at the end, that simply means there's an ionizable bond, and it's going to form a significant concentration of H3O plus. Now, we're not going to talk about equilibria in 110. In general chemistry, you will. And of course, you'll love it. But we'll talk just a little bit about enough of the basics so that we can understand the concept. This reaction is going this way and this way at the same time, right? What if it goes this direction 10 times faster than it does this one? That means that if you took a snapshot, you would have more hydronium and F minus than you would this stuff, because it's going 10 times faster this way than that way. This is the position of the equilibrium. And this allows us to define acids, things that make H+, into two very broad categories. We will call these strong acids and weak acids. Now at 110, we're only going to deal with strong acids. With a strong acid, it goes this way, maybe 10,000 times faster than it does back. With a weak acid, it's just the opposite. The back reaction is 10,000, and this is 1. So with a weak acid, you have mostly this stuff. With a strong acid, you have mostly this stuff. Once again, we're only going to really talk about strong acids in 110. Let's look at a little quick movie here. Oh, Yeah, let me say this. This whole thing of acidity and whatever is governed by several theories, described by several theories. The one that we're going to use, that we're going to talk about, is called the Bronsted acid-base theory. It's the simplest concept. Bronsted acid is simply defined as a proton donor. Now, why do we call it a proton donor? Because remember when we saw the movie, the little clip of the hydrogen being handed, it came over with no electrons. It had no electrons. So a hydrogen with no electrons is what? It's just a proton. This is called proton transfer. So the proton donor is the acid. The proton acceptor, the thing that accepts the proton, is called a Bronsted base. Very simple concept. Acid donates a proton, base accepts it. All right. Strong acids, HCl, nitric, sulfuric acid, whatever. These are strong acids. That means that the equilibrium lies almost entirely on this side. So instead of 10,000, I'm going to say like 1,000,000,000 to 1 in terms of how fast each one is. If you take HCl and put it in water, it essentially totally dissociates into hydronium and chloride. And if you don't believe me,
a strong electrolyte is a compound that ionizes completely in solution. Hydrogen chloride breaks into hydrogen and chlorine ions.
now the problem with this is that she's a little bit wrong. She should have had 1,000,000,000 little thingies here. And there would be one out of the whole mix, out of the whole 1,000,000,000, that was still HCl. That's what an equilibrium means. And for this case, a strong acid, you think virtually 100% hydronium plus an anion. Now the strong acids that we deal with, hydrochloric, we've seen that. Polar covalent bond, we can split it, hydronium and chloride. We've used nitric acid in the lab. This is nitric acid. This is nitrate, NO3, and we put the hydrogen on one of the oxygens. That's a polar covalent bond. Water can split it. We get hydronium and nitrate. We have it used for chloric acid, but it looks like this. ClO4, hydrogen on one of the oxygens. Again, polar covalent bond, hydronium and chlorate. In water, these are all at least 1,000,000,000 to 1. If you make hydronium, you're an acid. Now everybody's favorite acid, these are called monoprotic. That's a fancy word for saying they only have one hydrogen to give up. Everybody's favorite acid, of course, is sulfuric. This is what it looks like. We put hydrogens on 2 of the oxygens. So that's H2SO4. We can take them off one at a time. First one comes off, we get hydrogen sulfate. This still has a polar covalent bond. It loses another hydrogen to make sulfate and 2 moles of hydronium. 2 moles of hydronium, we call this diprotic. 2 protons. Any questions? All right, let's struggle through a little bit more nomenclature here. When we have things that are ionizing, Bronsted acids, Bronsted bases, whatever, we use a set of terms to describe these. These are going to be conjugate acid-base pairs. And once again, this is a fairly simple concept. We're going to look at an ionization reaction, and we're going to define the acid. We're going to ask, what happens when this guy loses its proton? Well, when it loses its proton, it forms the conjugate base. Simple thing to remember. A conjugate acid will lose its proton, makes hydronium from it, and it forms the conjugate base. So if we have nitric acid and water, in the Bronsted sense, the acid is going to be nitric acid. And you ask, what accepts the proton? Well, water does. But the conjugate base of nitric acid is going to be nitrate. The conjugate acid loses a proton. And what does it form? It forms its conjugate base. If you do the bookkeeping, conjugate base has one less proton. Typically that means it has one more negative charge, but that's not always the case. Always it will have one less proton because the acid loses it to form the base. Slightly different nomenclature than Bronsted. Any questions? Look at these. Identify in each the conjugate acid-base pair. With HCl and water, what donates the proton? HCl does. And when it loses this proton, what does it form? Chloride. This is the conjugate acid-base pair. Acid loses a proton, forms its conjugate base. They have the same numbers and types of atoms except for one, hydrogen. That's how you can pick them apart. Go ahead, look at the next one where you can't see it. Look at, this is the first dissociation of sulfuric acid. What is the conjugate acid-base pair? Well, you look at your equation and you say, what donates the proton? Sulfuric acid. Once you lose the proton, what do you make? Hydrogen sulfate. That's the acid-base pair. For the second ionization of sulfuric acid, what donates the proton? Hydrogen sulfate. What does it form? Sulfate. That is the conjugate acid-base pair. See, it's a really simple concept. Different than the Bronsted acid-base, but a very simple concept nonetheless. The last one. This one is different. Here we have nitric acid in liquid ammonia, of all things. Now, liquid ammonia has many of the properties of water, but not all of them. It's not nearly as good at doing anything that water is. It is conceivable, however, that if you had oceans of liquid ammonia, you could have some sort of life based on that instead of water. Conceivable. Not easy, though. All right, so in this reaction, what is the conjugate acid-base pair for the forward reaction?
Hydrogen and nitrogen.
Sure, we're going to do nitric acid. It's going to lose a proton and form nitrate. Now, these reactions go this way and that way, don't they? The forward reaction and the back reaction, we call them. Look at the back reaction. The back reaction. For going this way, what is our proton donor? And what is its conjugate base? Ammonium, yes. This guy is going to donate a proton to nitrate to form ammonia. Forward reaction, back reaction. That's kind of neat, right? Now there's a tutorial on this. Basically, the tutorial will give you an equation for an acid-base reaction. There'll be spots missing for you to put something in. Remember, don't worry about subscripts, just write numbers and letters. No charges, numbers and letters, that's it. Yeah.
Is there this is on one, right?
Yep, one of our tutorials. What we're supposed to put in these blanks here, we're supposed to complete this equation. Just a hint, as we look at it on this side, we have fluorine and hydronium. Do them in the same order here. That works best. Okay? All right, so the first thing you want to do is look at this and say, this is an acid-base reaction. We're making hydronium, right? Let's identify the acid component. What lost a proton to form fluoride and hydronium? The conjugate acid of HF is going to have one extra proton, isn't it? I'm sorry, F minus. HF is the answer. This is going to have one extra proton. What loses a proton to make F minus is HF. This is the conjugate acid-base pair. Now, for the forward reaction here, what is the Bronsted base? What accepts the proton from HF? Water, absolutely. H2O accepts a proton, that's our Bronsted base, and we get hydronium. Let's do another one. Here we're looking for the products. We have ClO3 minus and hydronium. Take a second, think about what the products of this reaction are going to be. Now the logic. ClO3 is a conjugate base to what? If you put a proton on ClO3 minus, what would you have? You would have its conjugate acid, wouldn't you? So ClO3 minus plus a proton gives us HClO3, chloric acid. When the Bronsted acid donates the proton to the Bronsted base, what's left here? Water. This is so simple. Do one more. Go ahead and fill this in. Very much like the last one. Here we have hydrogen sulfite and hydronium. What is the conjugate acid of hydrogen sulfite? We're going to take hydrogen sulfite, put a proton on it, and we're going to get H2SO3. If this is our Bronsted acid and it loses its proton, what does it make? It makes water again. Nice and simple. Any question? Well, we talked about strong acids, right? Doesn't it seem fair that we have something called strong bases? Of course it does. If a strong acid is almost entirely hydronium and a cation of some sort or anion in solution, it would make sense that a strong base starts off with an OH group on one side, hydroxide, and ionizes virtually 100% to a cation and hydroxide. Once again, whenever we say acid, we think of hydronium. That's what makes it an acid. When we think of a base, we think of hydroxide. Now, what happens if a hydroxide just happens to be floating around and finds a hydronium? Well, it can accept the proton from H3O, and we wind up with two waters. Way to think about this is if we had a solution of a strong acid and we added exactly the right amount of a strong base, what would we have? Water.
So bases are good.
Bases are OH minus, okay? They can accept the proton, and when they do, it makes water. When hydronium loses its proton, it makes water. 2 moles of water. And if it's only water, that is a neutral water solution. Here's a little cute diagram, a little thingy. Let's pretend we had HCl and water. So here's our hydronium ion sitting here in the middle. And we also have chloride somewhere. All right, they're all just bouncing around in solution. To that, I'm going to add sodium hydroxide. When I do this, the hydroxide will react with the hydronium to make 2 waters, and the sodium just goes along for the ride. That was so much fun. Let's do it again. Hydroxide is going to react with hydronium, and this just goes along for the ride. 2 waters. All right, so we start off here, let's go back again, with a strong acid solution, a strong base solution, and we wound up with a salt, sodium chloride, and water. This is a neutral solution. But remember, whenever you have a neutral solution, that is nothing but pure water. What do you have in there? You always have 10 to the minus 7 molar hydronium and hydroxide. That's in a neutral solution. You always have 10 to the minus 7 molar of each. Any questions? Let's look at a problem here. In general chemistry, you will spend a great deal of time doing what are called acid-base titrations. In an acid-base titration, you're trying to find the concentration of something. Okay? And you do this very quantitatively. We'll mention this, how you do it in a second. But this is just a sample problem. We're not going to do this in 110, but just so you get a feel for what we're doing here in real life. Let's say that we had a 0.025 molar solution and we had 125 mils of it. Okay? So we have a concentration and a volume. We remember that that means we know how many moles of sodium hydroxide we have. Now we also have a hydrochloric acid solution. When we mix these two together to get a totally neutral solution, we find that it takes 125 mils to do it. The question in a titration is, what is the molar concentration of our hydrochloric acid solution? Okay? How do we do this? According to our equation, 1 mole of HCl, 1 mole of sodium hydroxide. So it's easy. We know a concentration and a volume of sodium hydroxide, so we know the number of moles of this we have. We know that it takes 1 mole of this for every mole of that, and we have a volume here. The way we would do this is just remember concentration times volume is moles. So moles of sodium hydroxide, concentration times volume. Liters go away, and that's how many moles we have. Now, this is moles of sodium hydroxide, right? But remember, the stoichiometry was 1:1. So how many moles of HCl did we react with? Exactly the same. Our moles of sodium hydroxide are quantitatively identical to our moles of HCl. Sorry. All right, so here we have moles and here we have liters. Moles per liter is what? Molarity. So this is how we would take a set of numbers like this and solve for an unknown molar concentration. Once again, we're not going to do this particular type of problem in 110. Excuse me, let me do something here. I have 4 sons. What can I say, okay? We're not going to do titration problems in 110, but in general chemistry, I assure you this is a staple of life. All right, let's look at some real exam questions. In this one, I asked you to select the pair of substances in which the acid is followed by its conjugate base. Now remember, what do we know about conjugate acid-base pairs? Conjugate acid will lose a proton. That's all it loses. And it forms the base. So that means everything else has to be the same except for the missing proton. H plus HCl. Well, H plus can't lose a proton, can it? Because it is 1. If NH3 lost a proton, what would it give? NH2. So that's not right. If HPO4 minus 2 lost its proton, it would be PO4 minus 3. Not that. If hydrogen carbonate loses its proton, what does it make? Carbonate. Once again, to get to this thing, you'd have to put a proton on, not take one off. You simply lose a proton to form the conjugate base. Any questions? Another reaction here. Hydrogen carbonate plus water gives carbonate and H3O plus. Which of these statements is correct? Hydrogen carbonate is an acid, and water is its conjugate base. No. Water is functioning as the Bronsted base. The conjugate base has everything that this guy has except for a proton. So that's wrong. Hydrogen carbonate's an acid. Carbonate is its conjugate base. These two differ only by a hydrogen, and that is the correct answer. So let's look at the rest of these. Hydronium is an acid and hydrogen carbonate is its base. No, I mean, think about it. They have to have the same numbers and types of atoms right away, just missing a proton. So it's a very simple question. And one more simple one. The conjugate acid of hydrogen sulfate is what? This is the conjugate base, isn't it? Right? That's the conjugate base. The conjugate base was formed when the acid lost a proton. So which of these is hydrogen sulfate plus a proton? Well, it's sulfuric acid. Any questions?
Wait, what did we solve? I understand.
Well, you want to go back to that one? The conjugate acid. So that means that this is the conjugate base. The conjugate acid has one more proton. If we put another proton on, we have H2SO4. Yeah, she gets
I
it.
said C, so I did say B, so I was right the first time.
All right, let's go back to our concept of neutrality. Remember, we said that as water sits there, absolutely pure water, it's not pure. It has hydronium and hydroxide in it, right? How much? 1 times 10 to the minus 7 molar of each. Okay, that's in pure water. Now, this is an awfully small number. 1 times 10 to the minus 7. And just like for a very large number like a mole, 10 to the 23rd, we introduced the mole concept, right? Well, in order to deal more easily with very small numbers in terms of acids and bases, we're going to introduce the concept of pH. pH. pH is nothing more than the negative logarithm of the hydronium ion concentration. P is an abbreviation. It stands for negative log. What comes after that is what we're talking about. The negative log of hydronium is the pH of the solution. Now, a base 10 logarithm, abbreviated log, is the exponent of the number that 10 must be raised to produce that number. Hard to say that smoothly, but we're really talking about an exponent. 10 to some exponent, 10 to the x. For example, if we had 10 squared, 10 times 10, the exponent here for 10 is 2. The logarithm of 100 is 2. Is simply that exponent. If you pulled out your calculator, and you should, and you typed in 100, and you hit the log button, the answer would be 2. It's simply the exponent. If we had 10 times 10 times 10, that's 10 to the third. That's 1,000. The logarithm of 1,000 is just that exponent. So the logarithm of 1,000 is 3. Now, it doesn't have to be an even number or integer. If we say 10 to the 2.5, that's difficult to conceive without log tables or a calculator. But if you type in 10 to the 2.5 on your calculator, you'll see it's 2.5. Log of 316 is 2.5. So here we are going to learn to use our scientific calculators to calculate the logarithm of hydronium. And going back, if we have a hydronium, calculate pH. Let's start off with something very simple, though. Oh, I just wanted to point out, when you put something in brackets like this, little square brackets, not parentheses, square brackets, that's chemistry shorthand for molar concentration. So this is the molar concentration of hydronium. Its negative log is pH. All right, remember what we said about pure water. How much hydronium do we have in pure water? 1 times 10 to the minus 7 molar, right? What would the log of 10 to the minus 7 molar be? It would be minus 7. We multiply that by minus 1, and pure water has a pH of 7. That's where pH 7 comes from. Pure water has 10 to the minus 7 molar hydronium. Take your calculator and try it. Type in 1 times 10 to the minus 7. Hit the log button. You should get minus 7. Simply change the sign to get the pH. Now, if you have a solution where hydronium is greater than 10 to the minus 7, so you have a lot of hydronium, that's an acidic solution. If the pH is less than 7, that means you have an acidic solution. If the pH is greater than 7, you have a basic solution. And if it's exactly 7, you have a neutral solution. A small pH means acid. A high pH means base.
Can you show that again? How do you figure out the log? Is it 10?
We're going to actually do a log calculation in just a second.
It's 1 times 10 to the negative 7 power.
Right. 1 times 10 to the, take your calculator. Type in 1 times 10 to the minus 7. Hit the log button. It should give you minus 7. To get the pH, you change the sign to this minus log. Therefore, that's pH 7. If we have more hydronium, it's acidic, the pH is smaller. If we have less hydronium, it's basic, and the pH is larger. Now again, being fair, if we have a pH scale, we really should have a pOH scale, shouldn't we? And we're going to define it exactly the same way. It's simply going to be the negative log of hydroxide concentration. Now, if we have neutral water, how much hydroxide do we have? 10 to the minus 7 molar. So, the pOH is going to be 7. The pH is going to be 7. This is one of the things you can count on in life. For any solution, the pOH and the pH added together will always be 14. Now this is a little less apparent, but because each of these guys is 10 to the minus 7, the product, hydronium times hydroxide, is always 10 to the minus 14. Those two are facts that you need to remember. Hydronium times hydroxide, anytime, anywhere, is going to be 1 times 10 to the minus 14. And pOH is always 14. Handy things to remember. All right. Let's say that we want to calculate hydronium or hydroxide, if we know one or the other. If we remember that hydronium times hydroxide is always 10 to the minus 14, we can always calculate the unknown quantity. So if I tell you that hydroxide is 5 times 10 to the minus 8, what is hydronium? We know hydroxide. We know this, that's a constant. So we simply divide 10 to the minus 14 by this guy. And this is our hydronium ion concentration. Two simple things that will make life much simpler for you. Remember, hydronium times hydroxide is 10 to the minus 14. And pH plus pOH is 14. All right, let's give our brain a chance to unwind here. Let's do something descriptive. Let's talk about the pH scale. pH scale actually can go negative and can go over 14, but we typically think of it as between 0 and 14. If we had 1 mole per liter of HCl, that would be a pH of 0. If the pH is 0, pOH would have to be minus 14. Up here, if we have 1 molar hydroxide, that's a pH of 14. So the pH must be 0, because they have to add up to 14. Let's see. Stomach acid is down here between 1 and 2. Amazing it doesn't dissolve itself. Cola, bad wine, about 3. Very bad coffee, about 5. Blood, sweat, and tears, a little over 7. Work up here to ammonia and bleach, 12, 13. Again, anything above 7 is a base. Anything below 7 is an acid. In the lab, how do you measure pH? Well, you probably won't use one of these. This is called a pH meter. The electronics are simply a millivolt meter or less. This little probe right here is what you put in your solution to actually measure the pH. The thing about this probe is that it has a glass bulb on the end. The glass bulb, the thickness of that is less than a human hair. So it is really fragile. And they cost between $100 and $200 each. And it is not uncommon to see a student take this and smash it into the bottom of the beaker. Therefore, you're not going to use one of these. Not for a very long time. Back at UIC, we used to go through half a dozen a week. In my lab, not in the undergraduate lab. Just, yeah. All right, so this is a pH meter. You can stick it in a solution and directly read out a pH value. Very simple. This is a miracle called pH paper. pH paper is a bit of an engineering thing where various indicators are put onto a strip of paper, a mixture of them. So you take this and you dip it in your solution, and it will turn either red or dark blue, depending upon the pH. It's actually a really, really neat sort of thing. The indicators that we use. Indicators are compounds, mostly organic compounds, that change color depending upon the pH. So to make pH paper, you have to pick out a set, combine them in just the right ratio, so that you can get different colors for every unique pH. The one that we use, actually you've used this in lab, phenolphthalein, that's this guy. In acidic solution, it is colorless. And when you hit about 8 or 9, it turns this lovely shade of purplish pink. Very common indicator. Start off with a solution that's acidic. As you add base, nothing, 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 and pink. So that's how you know you have a neutral solution. Now, chemists are very clever to develop all this stuff. Yes, we are. But the cabbage beat us to it. Turns out if you take red cabbage and you squeeze it and get the juice out, red cabbage juice is also a natural pH indicator. In acidic solution, it's this rich red, more or less neutrality, it's kind of a purple. As it gets more alkaline, it's a blue. And when it gets fairly basic, it's an ugly green. Now, I don't know if any of you cook, but cooking cabbage is a staple sort of thing. You chop it up, you saute it, put stuff in it, blah, blah, blah. It's good. It's good. But if you remember that this is an indicator, you have to be careful what you put in it. This is kind of what nice cooked cabbage looks like. It's a blue-purple sort of stuff. Yeah, based on that. Nice and neutral. If, however, you decided you wanted a little more tang and you put in some vinegar, you would get cabbage that looked like that. And if you wanted to be bizarre, and you sprinkled in a little bit of baking soda, that's what your cooked cabbage would look like. So you got to remember the chemistry as you cook this stuff. Any question? Well, like I said, one of the great exercises in general chemistry is a process of titration. It's a neutralization experiment. We talked about a problem, how you can figure out the concentration, blah, blah, blah. Well, how do you know when you've added exactly 1 mole of stuff? You use an indicator. In this case, we're going to use phenolphthalein. This is called a burette. It's got a little stopcock here on the end. This is all labeled off in milliliters, so you can read your initial volume, you can read your final volume, and you have your sample down here with the indicator in it. So let's pretend that we're starting off here with an acidic solution, and our indicator is colorless. What you do is very carefully open the stopcock, let a little bit of stuff come running out. When you get your color change, you stop it. Look at your initial reading, your final reading. This tells you what volume you've added, and that allows you to calculate concentration. Once again, this is a staple in general chemistry. You will do titrations all the time. Any question on the concept here? All right. Take out your calculators and let's do this. I tell you that I have a solution that has a pH of 7.23. What is my hydronium ion concentration? Well, we remember the definition of pH is simply the negative log of hydronium. So, first thing I would do is get rid of this minus sign here. I'm not a negative person. So we're going to multiply both sides by -1, get the minus sign over here. So we have minus pH is log hydronium. Now, recall that a logarithm is simply a power of 10, isn't it? So if we take what's called the antilog, the antilog of a log, well, it just disappears, like matter, antimatter. Poof, it's gone. But the antilog of this number on this side winds up as an exponent. Simple thing to remember, the simple thing to remember, to write on the back of your hand. 10 to the minus pH is hydronium. 10 to the minus pH is hydronium. So we simply substitute in here. We're going to do 10 to the minus 7.23 to get hydronium. Now, everybody's calculator is different. Okay? Everybody's is different. This is what mine looks like. I look up here in the corner and I have a button labeled log. And above that, in little letters, I have 10 to the x. In order to do 10 to the x, I have to hit the green button first. That's just what I have to do. All right, what I want to do is 10 to the minus 7.23. So I type in minus 7.23. Now, I go and I hit my little green button, and then I hit this guy, and I get 5.888, whatever, times 10 to the minus 8. That is the hydronium ion concentration. One more time on my calculator. Type in the minus pH, hit 10 to the x, and that number directly is the hydronium ion concentration. Now that's not so bad, is it? Look at these guys. Quickly give me hydronium for each of them. The first two, of course, you can do in your head, can't you? If our pH is 4, we're going to do 10 to the minus pH, which is 10 to the minus 4. What is that? That's hydronium. Our next one, pH is 12. So we're talking what? Minus 12. 10 to the minus pH is 10 to the minus 12. Our hydronium, simply 10 to the minus 12 mole. Now you have to think a little bit more. pH of 5.5, you have to type in minus 5.5 on your calculator. Hit 10 to the x. 3.2 times 10 to the minus 6. A pH of 1.32. What do we type in? Minus 1.32. And hit 10 to the x.
Where'd you get 3.2 from?
Ten to the minus pH, 10 to the minus 1.32, 4.8 times 10 to the minus 2. Now it's a real bother on your calculator, but if I said we had 7.025567 as our pH, all you have to do is change the sign, type it in, 10 to the minus 7.02 blah, 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 and you should get about 9.4 times 10 to the minus 8. Now let's look at these. Which of these solutions are acidic? Remember, if the pH is less than 7, it's acidic. If it's over 7, it's basic. So acidic, basic, acidic, acidic. What is this? That's over 7.
Over 7.
It's basic, by just a tiny bit. All right, so let's do this the other way now. Here I give you hydronium. What's the pH? Here you're going to use your log button. Here's our given. Hydronium, 7.042 times 10 to the minus 7. We remember that the negative log of hydronium is pH. So we simply take the negative log of both sides. We get pH on this side, negative log of our hydronium on this side. So what do? Pull out our calculator again. What are we going to type in? 7.04 times 10 to the minus 7. That's our hydronium. And what do we do next? All you have to do is hit the log button right there. And it's minus 6.15. Remember, pH is the negative of that number, so our pH is 6.15. Type in the concentration, hit log, change the sign, you've got pH. You see, you all had to buy these scientific calculators, and you finally get to use the log button. Isn't that nice? All right, quickly convert these hydroniums into pH values. If hydronium is 1 times 10 to the minus 4, you type in 1 times 10 to the minus 4 on your calculator, hit the log button, change the sign, pH is 4. Type in 5.5 times 10 to the minus 4. Hit the log button, change the sign, 3.301. Type in 1.37 times 10 to the minus 8. Hit the log button. Change the sign. 7.8. Now this one, I'll be honest with you, I put on an exam. The question was, is this an acidic solution, a neutral solution, or basic? 7 times 10 to the minus 7. Everybody wanted to say neutral. You just did. What is neutral? 1 times 10 to the minus 7. Type this in. Hit the log button. Change the sign. 6.15. This is slightly acidic, isn't it? And our last one, 4.61 times 10 to the minus 5. Simply type it in, hit log, change the sign, and we're 4.33. Yeah? Significant figures. I have deliberately not talked about significant figures because it's confusing. I will just tell you, when you have a logarithm, the digit in front refers to an exponent. Remember, in scientific notation, we don't count exponents as significant figures. The back half of this, everything after the decimal, is called the mantissa. This has the same significant figures. So you ignore everything in front. This has 4 significant figures in the measurement. But we're not worried about that. All right, of course there's a tutorial. What's the pH if hydroxide is 6 times 10 to the minus 11? Oh my gosh. In order to figure out the pH, we need hydronium, don't we? Now, how do we figure out hydronium? Remember? Oh, what is it?
1 times 10 to the negative 7.
Shoot, hang on. This is what I wanted to come up here. Remember, under all conditions, hydroxide times hydronium is 10 to the minus 14. So remember that. Also remember pH plus POH is 14. So write those on your hand, and let's go back to where we were. We know hydroxide, that's given here, 6 times 10 to the minus 11. 10 to the minus 14 divided by that is this guy. Simply type in 1.64 times 10 to the minus 4, hit the log button, change the sign, and we get 3.79. Yeah.
Could you go back to the previous one?
Well, we are given hydroxide, right? We know that hydroxide times hydronium is always going to be 10 to the minus 14. Therefore, 10 to the minus 14 divided by this gives us hydronium. So, 10 to the minus 14 divided by our hydroxide, which is this, gives us a value of 1.6 times 10 to the minus 4. That is hydronium. If we know hydronium, just like we did on the previous set of problems, to convert this to pH, you simply type it in, hit log, change the sign, and it's 3.79. Let's do another one. Here we have hydronium. And we want to know pOH. Well, in order to get pOH, we need to know hydroxide, don't we? But we know that hydronium times hydroxide is 10 to the minus 14. So hydroxide is going to be 10 to the minus 14 divided by hydronium. 10 to the minus 14 divided by hydronium. This is hydroxide. How do we get pOH? Just like pH. Type it in. Hit log. Change the sign. It's 11.46. I think this is called pH 1. And if there's a pH 1, of course, there must be a pH 2. pH 2 is the type that most people really like. It's a table. Here you are given one value. And you have to fill in the 3 missing slots. Okay? Well, we're given a pH. Think about this. We know that 10 to the minus pH is going to give us hydronium. Right? We know that pH plus pOH must be 14. So we subtract this from 14. That gives us pOH. And finally, how do we get hydroxide? Well, we could use our 10 to the minus 14, or we could just simply say we know pOH. 10 to the minus pOH is hydroxide. So here's what I just said. To get pOH, we're going to take our pH, subtract it from 14, and we get 3.17. Everyone good with that? They always have to add up to 14. We know pH. To get hydronium, we simply need 10 to the minus pH. So we take our calculator, type in minus 10.83, hit 10 to the x, and it's 1.48 times 10 to the minus 11. Our last one, just like this one, we're looking for hydroxide. We know pOH, 10 to the minus pOH, 6 times 10 to the minus 4. Let's do one more. Here I am given hydronium. I know that if I took 10 to the minus 14 and divided it by this guy, I would get hydroxide. Correct? We know that. I also know that if I type in this guy into my calculator and hit log and change the sign, I get pH. Now I could take 14, subtract the pH and get pOH, or I could take OH, take its negative log and get pOH. That's what runs through my mind. For hydroxide, 10 to the minus 14 divided by hydronium, that's this stuff. Here's the numbers. Simple calculation, 8 times 10 to the minus 12. For pH, all you have to do is take hydronium, push the log button, and change the sign. 1.23 times 10 to the minus 3, hit log, change the sign. We're at pH 2.91. Yeah.
I was just going to say.
Once again, hydronium, type it in, hit the log button, change the sign, 2.91. Same basic operations. And pOH, we could simply subtract 291 from 14, that works. Or you could take the hydroxide, that's this guy, type it in the calculator, hit the log button, change the sign, and the pOH is 11.09. Any questions? This is an acquired skill. This was actually an extra credit problem on an old exam. Here we have a bottle of cheap red wine. It has a pH of 2.85. Trust me, you don't want to drink that. Calculate the concentrations of hydronium hydroxide and the pOH value. So exactly like the problems we've just been doing, except this was extra credit. So, how do we do this? To get hydronium, we know the pH. We know that 10 to the minus pH is hydronium. So you take your calculator, you type in minus 2.85 and hit 10 to the x. We're at 1.4 times 10 to the third. This should be minus 3, I'm sorry, molar. All right. Let's do pOH because that's so simple. We're given a pH. We know that 14 minus the pH must be the pOH. Take 14, subtract 2.85. The pOH, 11.15. And finally, hydroxide ion concentration. We could do this two ways. We could use the pOH, or we could use our 10 to the minus 14. Let's go ahead and just use the pOH. Hydroxide is going to be 10 to the minus pOH. So 10 to the minus 11.15. We type in minus 11.15, hit 10 to the x, and we're at 7 times 10 to the minus 12. Any questions? All right. We have 3 new tutorials: conjugate acid base, pH, and pH2. Remember, don't change the email address, put your name in, and earn with your extra credits. Any questions? Chapter 9 is going to be gas laws. Once again, this is going to be computational. So we have one more to get through. But the last one, chapter 12, is organic chemistry, and that's really fun. So, let's see, today is Wednesday, right? Have a good weekend, and I'll see you on Monday.